Okay, yeah, thanks, Kiara, for the introduction, and yeah, I hope everyone's got their coffee. Great. So, yeah, this is really going to be a talk about circumpolar deep water in the Southern Ocean, but from a glaciologist's perspective. I'm not really an oceanographer, but as you'll see, circumpolar deep water is a very important water mass for glaciologists to think about. And this work really started in the TIPAX project, which is now finished. This is a tipping point in Antarctic climate components, and yeah, it's continuing in, at least from my point of view, in a slightly different vein in the Ocean Ice project as well. And that's still ongoing. And this is work we've done with lots of different colleagues in Europe, but mostly with Petra Langebroek in NORCE and Bergen. So I'm not sure who's going to come to this talk. So I thought I'd start with either a very, very quick reminder or a very, very quick introduction about where is circumpolar deep water and why does it matter. So if I have a look at this very sort of simplified schematic of the global ocean currents, you can see there's this really major ocean current going round and round Antarctica in the Southern Ocean. And this is where we find circumpolar deep water. It's not at the surface, it's sitting above the Antarctic bottom water, which is the very, very deepest water, and then underneath the lighter surface waters. So it's kind of sandwiched in between bottom water and lighter surface waters. And it's pretty much circulating eastwards around Antarctica, kind of unimpeded really by any land. And it's relatively warm compared to other Southern Ocean water masses. I think if you were to fill a bath with it and get in, you'd probably find it wasn't very warm. But if you're the Antarctic Ice Sheet, then it is quite warm. It's still got some heat energy to do some melting. So yes, so if it's a major water mass, at least in the Southern Ocean. But as well as going round and round Antarctica, there's also a little bit of it transported southwards towards Antarctica. And this southwards transport is driven by partly by the wind and partly by bathymetric steering on the bottom of the ocean. And this southwards component of the transport is very, very important because it's taken heat from the Southern Ocean, and in some places this warmer water is getting onto the continental shelf around Antarctica, and from there it can get right into the ocean cavities underneath the floating ice shelves around the ice sheet edge, where it's got still enough heat energy to do some quite significant melting. And actually, if you look at the mass budget for Antarctica, about half of the ice is lost from Antarctica by iceberg calving, but the other half is lost by basal melting beneath ice shelves, and the heat for that basal melting really comes from circumpolar deep water. So this is a really important water mass for Antarctica. And of course, if circumpolar deep water gets warmer, then potentially ice shelf melting can increase. But I say potentially because only if it continues to get transported under the ice shelf cavity. And this isn't happening everywhere. So in some places, if circumpolar deep water gets warmer, then it might change ice shelf melting. But there are certain important places in the ice sheet where the mass loss is very, very sensitive to this temperature of the circumpolar deep water. So yeah, if you get faster melting, then of course you get ice shelf thinning, and then in turn that can lead to thinning of the ice on the grounded part of the ice sheet. And once that happens, then that contributes to sea level rise. But also, of course, if there's more melting, then there's more fresh water being released into the Southern Ocean. And this makes the surface of the Southern Ocean a bit fresher, which changes the stratification, sea ice formation, deep water formation. So this extra fresh water can have quite wide-ranging climatic implications as well as the sea level problem. So I thought I'd start quickly with is circumpolar deep water getting warmer? Of course, we hear about lots of other parts of the planet which are getting warmer, but this is a bit hidden away, a long way from us, at least in Norway anyway. So one of the problems we have is a bit of a lack of long time series of circumpolar deep water temperatures. Because it's quite a sort of noisy time, there's a lot of sort of decadal variability, quite a lot of spatial variability in these changes. It's then hard to pick out significant trends in relatively short time series. But there are a couple of papers I thought it'd be worth highlighting. One is the CMIP6 paper, where they've got about 30 years of data from around Antarctica. And this little plot here shows the trend. So a warming trend where it's red, cooling trend where it's blue, and I think where there's a hatching that it's not statistically significant. But we can particularly see around to the left of this purple dashed line that around Antarctica there's really a weak but statistically significant warming trend in most places. And this is important because this is where there's lots of parts of Antarctica here where the ice loss rate is very sensitive to water temperature. So we've got warming in the places that it really matters. And then another interesting paper was this Service-Strahl transect, and this is just from one transect across from Antarctica to Tasmania. I think I've put the purple line in roughly the right place. Hopefully it is. And here again, there's a very weak warming trend of about 0.06 degrees per decade. I'd be a bit hesitant to put a linear trend for all of that time series, but this is a ballpark figure to work with. And that is actually quite similar to the warming trend in the CMIP6 paper around West Antarctica. So I think looking at least those two studies, if we were wanting to get a rough indication of recent warming in this sort of historical observations period, then around 0.05 degrees per decade, and at least in the places which really matter. Obviously, there's high uncertainty in there because of the variability and some spatial changes as well. But just for a ballpark figure to work with. So bearing that in mind, it's quite interesting to look back in time quite a lot further and see how does that compare to what's happened in the past. And an interesting period to look at really is the Quaternary, or particularly the last part of the Quaternary, which is the last 2.5 million years. And during this time, Earth's climate has really gone up and down very dramatically between these very cold ice ages, which are glacial periods, separated by lots of warmer interglacials. And in particular, I'm just going to get rid of this box here. Yeah, in particular, there's been the Holocene, which is the last 10,000 years. That's the current interglacial that we're in now. And then there's the last interglacial about 120,000 years ago. That's been quite a popular period to study by paleoclimate people, looking at the Earth's response to warmer climates. And then a little bit further back again, 400,000 years ago, marine isotope stage 11, which is quite a long, warm interglacial. And then before that, we had a period of sort of cooler interglacials, which were a little bit cooler than present. And these all show up very nicely in this air temperature reconstruction from the middle of Antarctica, based on an ice core. And that's really one of the best archives of past conditions we have, I think, at least in this period. But if we want to know what's happened to circumpolar deep water during this time, we don't really have anything quite as good as this air temperature record, unfortunately. But what we do have is some evidence from marine sediments, and In particular, we can use these little creatures called benthic foraminifera, and these are tiny organisms, just single cells, which inhabit the seabed. They come in all sorts of weird and wonderful shapes and sizes. And I've just picked out this one slide here with some very funky looking creatures on it. And this is a Vigorina, one of the forams we use for bottom water temperature reconstructions. But there's lots of other different forams as well. A lot of them look like sort of blobby snails. But importantly for us, they develop these calcite shells. And these calcite shells preserve some of the environmental information about conditions that they were living in. And gradually over time, the shells become buried by more and more sediments above them. They're not always preserved, but if they are preserved as fossils, then they can be eventually recovered in marine sediment cores. And these just basically, you can see on the left-hand side, you can extract these cores, and they're you can see all the layers, and many different layers of mud, different colours. I guess this is very expensive mud when you think about how difficult it is to get it. And then so we can analyse lots and lots of different environmental information in these cores. And for us, there's two important proxies which you can use based on this calcite shells. One is the magnesium-calcium ratio. So if you think of calcium as being calcium carbonate, some of the calcium is substituted by magnesium. And the amount of magnesium depends mainly on temperature and a few other factors. So that's one way we can try and reconstruct temperature. Otherwise, there's the oxygen isotopic composition of the oxygen in the calcite. And this depends quite strongly on two main factors. One is the water temperature again, which is how we use it. The other one is the ambient seawater oxygen isotopic composition. And that seawater isotopic composition depends quite strongly on the volume of the Earth's ice sheets. So we have to, if we want to reconstruct temperature by itself, we have to try and deconvolve it from the ice volume signal, which is not that straightforward and does lead to some other important uncertainties, especially since the two tend to be quite well correlated anyway. But if we can use both those proxies, they have quite independent errors. So averaging over two is a lot better than just one. So I mentioned at the start that circumpolar deep water is kind of sandwiched a little bit between Antarctic bottom water and some shallower water masses. This is a little bit of a problem for us because if we want to reconstruct circumpolar deep water temperature from organisms that live on the seafloor, we can't do it everywhere because sometimes there's Antarctic bottom water at the seafloor. So we have to go to places where the bathymetry is sticking up through the Antarctic bottom water and into the overlying circumpolar deep water. So that already limits the places that are available quite a lot. But if we look at places around the Southern Ocean, there are, I think, 6 sites we found where we think that the seabed is best represented by circumpolar deep water. All of these 6 sites have oxygen isotope records back for at least one glacial cycle, so at least about 100,000 years. 2 of these sites also have magnesium-calcium records, so that's also very helpful. And what we can do, because each individual site has quite high uncertainties, if we want to look at changes over long time periods, it's quite good just to average them all together and look at a sort of whole synthesis of the region. And so to do this, what I've done here is, sorry to copy this horrible plot, but in the top box, I've just plotted all of the data for all of the 6 sites. And in this case, it's the temperature anomaly at each of those 6 sites every 4,000 years through the last 800,000 years. And we can't really get the temporal resolution any better than 4,000 years because there's just not enough data really. So that low resolution does smooth out some peaks. And I've also plotted again this Antarctic air temperature time series, and this time it's been resampled to 4,000 years to match the same resolution as the temperature, the Circumpolar Deep Water temperature time series. And you can see that this record is quite scattered, but if you look at the average, which is the black line that's just about visible over all the little blue points, it does show the clear cycles of interglacials and glacials, and it's actually very well correlated with the Antarctic temperature time series. Both the timings of the peaks and the magnitudes of the peaks match quite well. The only difference really is that the range of temperatures is much lower for the Circumpolar Deep Water. And I think the important points really are that if you look at the peaks of interglacial warming, it's peaking at around half a degree above present in the warmest interglacials, and then cooling by about 1.5 to 2 degrees in the glacial periods. But I think if we were to try and look at this at higher resolution, which I've managed to do in a couple of the interglacials, we'd find that the interglacial warming is probably closer to 1 degree. It's just it gets a little bit smoothed out when you look at low resolution. So if we then summarize that, really, yeah, about half a degree of warming in interglacials, or in the warmest interglacials in the last million years, or nearly a million years, maybe closer to a degree if we were looking at slightly higher resolution. So based on that, you can already see that the current warming of circumpolar deep water in the historical period, although it doesn't sound very much, it's potentially, if it continues for a few decades, it's quite a lot of warming in comparison to what we've seen in the last million years or so. So the next question then is, what's going to happen next in the next 100 years or a bit longer? So I think for this question, we really have to rely on climate simulations to estimate changes in future circumpolar deep water temperature. And there's two important forcings to think about. Is the change in greenhouse gases and all this kind of anthropogenic driven climate change. And for that, we can look at the CMIP6 type simulations based on different emission scenarios. But as I also mentioned, that the freshwater coming from the increasing ice shelf melt, this is also an important control on the oceanography in the Southern Ocean. So it's also good to look at experiments that have explored what happens when you add more fresh water into the Southern Ocean. And these are classically called hosing experiments. So yeah, these are two important forcings we can think about if we want to think what's going to happen to circumpolar deep water temperatures in the coming century or so. So starting with the greenhouse gas forcing, there's this really nice paper by Purick in England summarising the CMIP6 models and how they might represent circumpolar deep water in the coming, or during the historical period, and then in future scenarios. And in their case, they've started with some validation, which is quite nice to see how well do Earth system models simulate the Southern Ocean at the moment, because of course we've got observations that we can validate them with. So first, if we compare the observed state of the Southern Ocean with the model state, then these plots here are they're cross sections across the Southern Ocean from south to north, averaged all the way around, so it's like a zonal mean. So this is obviously hiding a lot of regional variability that you get in different sectors, but it is giving a reasonable overview of how well are these models doing on a sort of almost qualitative level. And you can see that they're capturing the temperature pattern quite well, but the models are in some places quite a lot warmer than the observations. But if we look at the change through the historical periods, this is from the 50s to 2014 or so, then the models are actually capturing the changes in ocean temperature quite well. At least the multi-model mean is. Individual models vary a lot from this picture, but if we average across all 22 models, then that's doing quite well. So we can say that perhaps the temperature changes are modelled reasonably well in this part of the world. At least they have been for the last 60 years. And so on that basis, we could have a look at what the models are suggesting in the future. And these two scenarios, there's SSP245, there's like a sort of middle of the road scenario. And then there's SSP585, which is like an extreme warming scenario if emissions continue to increase. And in this case, particularly in SSP585, by 2100 at least, we could easily see 0.5 degree warming in circumpolar deep water. Again, there's really a lot of spread across these models if you look at them individually, but taking the average around typical levels of sort of circumpolar deep water at the continental shelf break, yeah, 0.5 degree is, I think, probably quite a realistic amount of warming. And again, this will vary around the different parts of Antarctica. So if we had time, we could look at different areas, but we haven't really got time just now. But if we went with 0.5 degree anyway by 2100, so 0.5 degree of warming would cause really a lot of extra melting of the Antarctic ice shelves. So then it becomes very important to think about how does that extra fresh water in turn affect the ocean temperature in this kind of feedback cycle. It could be negative or positive feedback, potentially. And so this is something that's been studied by a lot of different people. So I'm just going to pick out a couple of examples. One is this project, Southern Ocean Freshwater Input from Antarctica. And this is like a sort of informal community initiative, which runs quite conceptual experiments assessing how does Antarctic ice melt affect climate. And they're simple conceptual experiments, but it means that lots of different groups can participate, and it means that the results are very comparable from model to model. And in this case, their basic experiment increases the freshwater runoff from Antarctica by 0.1 sieverts, which is about roughly doubles the present day freshwater flux from the continent. And this extra water is added uniformly around the coast at the surface, so it's a very simple experiment, but it's it's easy to analyze results across lots of models. And there's no changes in CO2 emissions, so this is just using a pre-industrial climate. And in this case, when the first analysis was done, there were 7 different models that contributed to this experiment. And again, all 7 models showing qualitatively the same sort of response, where you get surface cooling and subsurface warming, different to different degrees and different extents between models, but the basic response is quite encouragingly consistent, I think. But if you look around, again, these are zonal means across the Southern Ocean, so it hides a lot of regional variability. But looking around about, say, 1,000 meters or so, close to the continental shelf, there's again, warming signal of 0.5 degrees or so in some models. So you can see how this could potentially cause positive feedback. So if the freshwater signal is causing warming of circumpolar deep water, but the CO2 forcing is also causing warming, then these can interact and positive feedback between more melting and more warming. And in another example, Gorter et al. They've added fresh water to one of the SSP scenarios, so SP585. So this is kind of looking at what's the effect of adding fresh water and the climate and the CO2 forcing together. In their case, they have used gradually increasing freshwater runoff from Antarctica, and by 2100 it triples from its present day runoff. And they haven't added it uniformly. Most of the extra fresh water has been added around West Antarctica, where they think most of the melting is going to occur. And in their case, this is plotted a little bit differently to the ones I've shown you already. But looking through time, the top plot shows the upper 200 meters, and the bottom plot shows from 200 meters to 5,000 meters depth. This is averaged all the way across the Southern Ocean, quite far north, I think, actually, maybe 40 degrees. And in the upper layers, the signal is quite mixed to start with, but then you can see there's gradual cooling by 2100. This is the anomaly relative to the CO2 only. So what they've done here is that the SSP585 simulation is like the control, and then the SSP585 plus the Antarctic freshwater is the experiment. So even though in this top plot it looks like there's cooling by 2100, it's only cooling relative to the warming scenario, if you see what I mean. So there's warming, but there's just less warming than would be without the freshwater. And then below 200 meters, the added freshwater enhances the warming that would already have been occurring in the SSP585 simulation. So yeah, if we look in the next 100 years and a bit beyond, which I haven't really shown you, sorry, then yeah, I think it's quite conceivable that the circumpolar deep water warming could easily match the warmest interglacials of the last million years. And I think with the positive feedback between warming and freshwater inputs, then potentially it could exceed it quite quickly. And I haven't got very much time actually, but I just wanted to really quickly run through what might be the effect on the Antarctic ice sheet of this temperature changes. And again, thinking back to this heat source of the Antarctic ice shelf and the melting, what would that do? And again, looking back in quite a long time period, we've run some Antarctic ice sheet simulations through the last 800,000 years. And to do this, we take the temperature anomaly from the Antarctic ice core record. We use a deep ocean temperature anomaly similar to the one I showed you, but it's a little older version which uses a different information source, and then the global mean sea level. And we use these three main forcings for Antarctic ice sheet evolution and run them through an ice sheet model to simulate what were the changes in ice volume through this period. And I haven't really got time to go quickly into lots of details, but essentially these top three time series show you the three forcings through the last 800,000 years. And then the bottom time series is the ice sheet response. And there's two sets of experiments here. The black wiggly line, that's just a transient ice sheet response that we simulate when we use these three forcings to simulate the ice sheet changes over time. And then at various points through this time series, we just keep the forcings constant at their instantaneous values, and then just run the ice sheet through to a steady state to see what is the steady state ice sheet for each of these different forcings. And that's the coloured dots show what is the corresponding steady state at each of these different times. So sometimes the steady state ice sheet is quite different to the transient ice sheet at that time, because the ice sheet has a very, very long response time to the forcing. And from the point of view of today, I think the sort of interesting points really are in the transient run, where we just model the evolution of the ice sheet based on these three forcings, in the three warmest interglacials of this past 800,000 years, the ice sheet has contributed about 5 meters sea level above what it is today. So this is because of ice loss in West Antarctica. But if we let the ice sheet run to steady state, then we actually get between 4 and 8 meters of sea level contribution with circumpolar deep water temperatures, which are only a quarter of a degree warmer than present. So I think in the context of the projected warming, this is quite a worrying result. So yes, I think I'm running out of time anyway, so I will leave it there. And I think, yeah, summary is really the circumpolar deep water is the main heat source for ice shelf melt in Antarctica. And looking back for 800,000 years, I would say that the likely peak really is between 0.5 and 1 degree C above present for the warmest interglacials. Last few decades, a little bit tricky to put a number on it because it's spatially variable and short time series, but I think in places it really matters. At the moment, around 0.05 degrees C warming per decade is a reasonable estimate. Future warming could easily see a 0.5 degree warming, I think, by 2100. Perhaps a lot more than that if there's a feedback from the Antarctic ice melt and the freshwater input. And then in some context, really only quarter of a degree warming is sufficient to cause more than 4 meters sea level rise through ice loss in West Antarctica. So I can stop there, and if there's some questions, I'm happy to take them.